In this example, we are going to use Green's theorem to find both counterclockwise circulation and outward flux for this vector field F, which equals x squared plus 4yi plus the quantity x plus y squared, j. And my curve C is a square bounded by x equals 0, x equals 1, y equals 0, and y equals 1. Or rather, C is this square here in the first quadrant. We are dealing with this region. And counterclockwise rotation would take us in that direction, starting at the origin. As we saw from the proof, the circulation and the outward flux, those are pretty straightforward calculations. So let's see, m here is x squared plus 4y. N is x plus y squared. I need the partial with respect to x and y for both m and m. So m partial with x, that is 2x. M partial with respect to y is 4. N partial with respect to x is 1. N partial with respect to y is 2y. So setting this up, my flux integral is the double integral along my over my square region, I should say, of m sub x, 2x, plus n sub y, 2y. That would be dA. Or rather, 0 to 1, 0 to 1, my bounds on x and y are the same. 2x plus 2y, so I will just define this dy dx. Working from the inside out, I have 0 to 1, that would be 2xy plus y squared from y equals 1 to y equals 0. Or the integral from 0 to 1, that gives me 2x plus 1 minus 0 minus 0. So I have 2x plus 1 dx, which is x squared plus x, evaluated from 1 to 0, which gives me 1 plus 1 minus 0, or 2. So my flux is 2, my outward flux. And calculating the counterclockwise circulation, similar integrals, the double integral over the region R. In this case, we have n sub x, which is 1, minus m sub y, which is 4, dA. Or 0, 1, 0, 1, negative 3, dy dx, which is negative 3 over that square region. What's the area of that square region? It's 1. So we have negative 3. Negative 3 represents my counterclockwise circulation. So that concludes our example where we used Green's theorem to find both the flux, we did the outward flux first, and then the counterclockwise circulation second.